I'll be spending some time on what's under the hood, and more specifically, Sri will show some of the customer visible insights, and Bern will spend more time on additional detail around the machine learning engines. Let's start with what's the key ingredient for good data science. It's actually the data. And for somebody that started on Wi-Fi machine learning about 6 years ago in RASA, starting RASA, I really appreciate how important the data is, because doing machine learning on thousands of devices is very hard. So going from thousands of devices to million plus that we have now has been great. We've been basically doubling the number of devices year over year. And by the way, we have stored all this information for the last 4 years, so we could find really interesting patterns versus time and very, very fine-grained anomalies. So the first thing, this unified cloud infrastructure that Ash talked about basically enables us to get information about switches, gateways, APs, and clients in a centralized location to do our modeling. Our telemetry is smart and streaming constantly. It includes things like state of the devices, the stats of all the links and all the ports, any events that we program to showcase any type of problem, all the configs for all the devices. Of course, this is a lot of information. We cannot send all this raw information. So we have intelligent edge preprocessing. 90-something% of the devices are happy and doing totally fine. So we don't need to have a lot of fine-grained information. So what we do is we do intelligent preprocessing, aggregate information that's not that important, and generate more events, more fine-grained information when something interesting happens. Our telemetry is very rich and diverse, as I mentioned. There's a lot of types of messages and fields, and it's very rich because we're collecting it from 1 million devices. One thing that often happens is that we try to build models. If we find that it's not as accurate as we like, or the root causes are not as fine-grained as we would like, we just basically push more a new software version that will actually enhance the telemetry to add additional fields or accuracy. And one more thing that we also do to make sure that the data is accurate is we have setups to actually do synthetic tests to inject known patterns into these devices to see if it could detect the telemetry correctly and how accurate the telemetry is itself. Because trying to build models that are 99% accurate, you need the telemetry itself to be close to that. So the type of telemetry we receive is around the infrastructure, as I mentioned, over 1 million devices and doubling year over year over the last 5 years. We basically start with thousands, and then as soon as we joined Aruba, we had 100,000 within months, and now it's about 1 million. And this includes telemetry around switching, gateways, and APs. Of course, APs dominate because there's a natural ratio between APs and switches and gateways. But the type of things we collect are all around a lot of Wi-Fi features, and here just a list of examples, a lot of switch type features, and a lot of WAN and gateway type features.
Jose, do you have any statistics on like the amount of data being collected, let's say per access point access point per second or anything like that?
Yes, the next slide mentions it's about 3 kilobits per second per device.
Okay.
So
sorry.
Yes, that's a good question. I mean, obviously, we're talking about a lot of telemetry. We don't get the WANs to get overloaded. So the step of intelligent preprocessing helps. Otherwise, it'll be probably a couple of orders of magnitude higher than that number, and then it will not be good. So another type of telemetry we get is around clients. And in the last year, we've seen 55 million unique clients collecting to this 1 million devices. And this is important for building device fingerprinting profile models, because there's a lot of Wi-Fi has been around for 20 years, and we're using basically the same spectrum and 5 or 6 different standards of devices interoperating in the same band. So we basically, this very big database of clients over the last 4+ years has things about all the quirks, all the mobility states, the capabilities, all type of Wi-Fi little IEs that they're capable or not capable of, and all the little interoperability. They have issues that they may have with beacon rates, issues they may have with specific channels, issues with specific bandwidths. So we have all that information. So when we make recommendations, we make sure your clients will stay connected. And then the third stool is the customers. The fact that we have 65,000 customers on Central, that means we get a very big diversity of configs. As I'll be talking about later, typically one customer has the same config pushed on every single AP. So they don't learn a lot. And then not like customers are going to start changing configs every few days and see which is the best for them. They can have one config, it kind of works. They don't know how far it is from optimal, but it works. And they're just going to stay there. But because we have all these customers in such diverse environments, we could actually recommend what's the optimal configuration for your environment based on peers.
What kind of, I have a question. What kind of feedback have you been receiving from your customers regarding AIOps? So what have they found beneficial on this?
So we've been doing this for 4+ years in Aruba. And the first set of customers were big campus customers that had typically between 3,000 and 15,000 access points. And we would actually, to improve the product, we would actually talk to each one of them every week or every month, depending on the customer. And they love this product because if you have a campus with 15,000 APs, you're probably going to have 2 configs, maybe dorms and then classrooms, and that's it. You can't optimize the config per environment. So we basically, and plus, the config that they have sometimes has been set 2 or 3 years ago when things like AX didn't exist. Actually, when we first started and 4 years ago, people had half the campus in 11N and half the campus in 11AC. And often the configs they have selected for 11AC APs were just copying the 11N and configs and just copying them over. And it led to very suboptimal type deployments. And by exposing them to new configs that other people that had 11AC, they could actually get best of breed configs for the new gear. So yes, now that we're in Central, we have 65,000 customers. So we're interacting mostly with the bigger ones. But as you could tell, well, I could tell, from the quality of the configs, you could tell that the bigger customers, the ones that have at least 1,000 APs under management, the configs have some intelligence in them. Customers below 1,000 APs, they just use the stock config. The one that the AP comes up by default with. They don't understand what these things are about, so they're just using the default configs out of the box. And it leads to very suboptimal configurations because it's not the same thing to have a fast food joint with one AP than to have a K through 12 with 50 to 100 or have a stadium with 1,000 APs. And just using the out-of-box config is very suboptimal for all those environments.
Hey, Jose, the one thing that I'd add as a response, sometimes going in there, you look at a large campus, college campus, like setting, not every building looks the same, right? The physical environment, there's enough variance in there that if you want to manage different configurations for different physical environments using human energy, it's not very efficient, right? It's not possible to hold everything in our heads in there. And that's one of the places where we've gotten very good feedback in being able to go in there and customize recommendations that are very specific to down to a building level or groups of APs, for example, is one. One of the early pieces of feedback that we got, I mean, we used to go in and say that, okay, once you turn on this capability, in a week or two, we'll start to tell you where your problems exist and how to resolve them. And I remember we went into one customer site where after 2 weeks, we couldn't find anything, any problems with them because the network was well designed and well run. But the feedback from the customers was that knowing that is actually also valuable because when there are no problem reports that hit help desk, it's not clear if end users are just losing interest and finding other ways to get things done, or if the network is really clean and is problem free. But even knowing that is sometimes useful to customers. That's another point of feedback that we've gotten. And before we go on this slide, I mean, to me, the complexity at the edge is not from potentially points of the infrastructure and the code that we have running on the infrastructure. It's all of the behaviors of clients that we have no control over, right? We have no control over how an Apple or a Samsung or a Microsoft tweaks their client behaviors. And to a large extent, our observations tell us that they're all optimizing for home environments, which are simpler environments in there versus those same behaviors are not necessarily optimal over here. getting an understanding of that and factoring that into making our recommendations is a very important aspect. And it's not something, it's something that is not necessarily, we don't necessarily amplify that as much as we need to, but it's an important config. And getting access to that, volume of client data helps us understand not just how the behaviors are with different categories of clients today, but how they evolve with time. Every time there's a new update, it brings with it certain new behaviors that we have to now adapt on how we respond to it on the algorithms that are built in on our side as well. And from a customer config perspective, given the volume of configs that we've seen already here, I don't want to go out and claim that we've seen every single corner case that is out there, but we've seen large amounts of corner cases. And again, those are getting factored in there. For you to identify something that doesn't occur very frequently, the only way to account for it is to get this large data set. And then you start to spot patterns that are not very frequent, right? If there's a problem that affects every single iPhone that's connected to the network, those are easy to spot. But if it only affects some strange, Nintendo Wii device that hasn't been updated for 5 years, for you to identify that requires the more the volume of the data set that we have access to, the better we're going to get at identifying many of those corner cases in there.
So I have a question about that intelligence. So when you talk about intelligence, it sounds like you're leveraging it specifically to improve the configuration of the devices, to improve the performance of the network. Is that what we're hearing, or have I missed something?
It also helps troubleshoot events in there, right? Ultimately, something shows up, and how do you resolve it? Sometimes those resolutions or configuration changes that happen to micro environments within the network. Sometimes it could be pointing to saying, we believe that. Essentially, if you look at an anomaly or a problem that shows up, the best way we can attempt to find root cause is to kind of segment it and say, okay, we believe that this is where you should start to look for root causes, and where the root cause exists within our domain, we can translate that resolution into a change, a config recommendation, or some change that we can recommend where it is outside of the domain that we directly control. Let's say, you've hit a wall with, a brick wall with respect to a AAA infrastructure, and that's where things are slowing down, or a DNS server that today isn't responding as quickly as it did yesterday. We can't directly fix those things, but we can at least guide them towards saying that's where you should start to look for resolution of the problem. So
right,
that's troubleshooting too.
Yeah, my question was, and I think you've answered it, but just to clarify, I was just trying to understand where you're focusing that intelligence, and it is around understanding when there might be configuration issues that will affect performance.
There's other variants, and I have more slides on different type of use cases. It's basically, think about a Swiss Army knife trying to solve problems. We have, with this very big data sets, we have found issues on Qualcomm and Broadcom chipsets that you could not find, they would not be able to find when they're running their own regressions and just checking each channel, each band in some compliance lab. But given that we have 500 million chips from Qualcomm, 500,000 chips from Qualcomm, 500,000 from Broadcom, we could find really esoteric problems like specific channels on the DFS band for specific bandwidth with specific clients doing something strange. And they cannot find those combinations. With big data, we're able to find them. And we've actually helped them fix their code. And they've had several workarounds over time based on some of these machine learning outputs. So as you probably know, these radar detectors are a little finicky on these chips. And sometimes these radar detectors have side effects on some other parts of their front end. So we found problems like that, but I have a little slide on improving our own software. We also find patterns on our software that we could improve for the next version of it. So
one question I might have, and I think it's kind of, it follows on from some of the stuff we've been talking about. How much of this is, deep learning, neural networking types of processing versus, machine learning, data analysis, data science kinds of things? or is it obviously it's a mixture of all that, but I'm just trying to understand where the neural networking, deep learning types of functionality, comes into existence in this ESB solution, I guess I'd call it.
So it's a combination of all the above. You don't want to build a model that's any more complex than you need to explain the outputs. So for some of these things, there's classifiers that are random forest or boosted trees type algorithms. And that's all you need to be able to say that this is an iPhone 14 with this quirk, or we don't need to go and do very deep things for those. And for example, to find that there's clusters around specific chipsets on specific environments, on specific bands, you don't need to use a deep network. You use clustering and classification type things. So it depends on the use case. And you don't want to find a use case that is simple and put a very complex model that you can explain. And it may be 99% fit, and then it spits out some really crazy outputs 1% of the time. So again, the model should not be more complex than the problem you're trying to solve.
Okay,
so it depends on the use case. Okay, so this is the next slide, just trying to layer in the progression. So as we mentioned earlier, there's the data input, about 3 kilobits per second per device, aggregated over 1 million plus devices, about 32 terabytes per day. We obviously do some intelligent compression. This is actually the raw data, but we don't actually pass 32 terabytes to the cloud every day. And this leads to, going back to your question, think about these as just toolbox or Swiss Army knife type things. This is not comprehensive. This is just 4 classes of type of things we do. Have a little more detail, and Sri and Bern will have additional detail. But one of the building blocks that we're very proud of is this peer group engine, which basically, for each environment, it looks at networking type parameters, client type parameters, and behavior of the clients in that environment, and tries to put them into peer groups. So right now we have 25 peer groups that classifies these environments into 25 things that are basically data science-like groups. We cannot exactly say this is a stadium and this is a classroom and this is a fast food restaurant. But we have these classes based on environmental features. Once we have these classes, when you put each customer can go build models against their peers. And once we have these baselines models, we could actually start detecting anomalies for that customer relative to its peers. These anomalies, as you're going to hear over and over again, are going to be very noisy. So you have to run some intelligent clustering on top of it to get some metrics around how bad these anomalies are before you start panicking everybody and people get anomaly fatigue. So this is like the first type of family of machine learning models. Then there's the recommendation type models, which for this, you actually need the cloud and you need to have a lot of diversity on the configs. And this is basically what it's doing is different environments have different configs and receive different performance. So you could build a model for each environment, each config was the right performance, and then you could optimize across configs for that environment. And then, of course, as Parth also said, these models have to be retrained constantly. Some of these models, like some of the baseline ones, might retrain every day. Some of these recommendation models we train every week, because we constantly have new clients, new technologies, new applications. If you think about optimizing models 6 months ago, Zoom would have not been the top application. So right now we want to know, how is Zoom performance relative to environment, relative to config?
So Jose, do you guys have customers that are taking this model or this approach and then integrating it with, let's say, Kubernetes operators to surface up for K8s operators overall improved operations for their private cloud or cloud services?
So these recommendations specifically go in multiple directions, but some go after customers to optimize the networking config here. Some of these models could go after the chipset supplier. Some could go after some of our AOS default parameter recommendations. For example, every AOS version, we have a set of defaults of how the AP should work out of the box if the user doesn't know better. So these recommendations.
So I guess I'm thinking beyond AP. I'm thinking about, because Aruba manages the entire portfolio for all of HPE networking. So as I'm thinking at this from a HPE networking perspective, if I'm running a cloud based on Kubernetes, and I do a CRD that says, hey, you know what, provision 18 new nodes, and the operator talks to the Aruba AI Insights platform, and the AI Insights platform says, you know what, yeah, I'll do that, but I'm going to do it in a special way because what you're requesting me to do requires a unique config. Are customers gotten that advanced, or is that more of, pie in the sky?
So the applications that we're going to be talking about today is not about optimizing their cloud resources and their private networks. It's about optimizing their network gear, their switches, their gateways, and their APs. The storage and compute type questions you're asking is not.
Oh, this is not even from a storage and compute. I'm talking about operators who's operating networks. So stuff that can the servers and when I provision 1,000 new hosts, that's going to require underlying network configuration change, whether it's VLANs, VXLANs, whatever the change. It requires new network configuration. And I want to do that programmatically. So I'm going to so let's eject the concept of Kubernetes. I'm going to make a programmatic change to an AP, to a set of network switches, etc. Do you guys have people who are using this as infrastructure as code type scenarios in which they're making changes, and this helps them make changes more intelligently?
I think I understand what Keith is asking, and I was going to ask something very related to that, which may answer Keith's question too, which is, can you talk about how customers are actually using this model retraining in practice? As opposed to the theory of it, how are customers actually leveraging this in practice?
We are doing the retraining. It's not the customers.
Customers are consuming this as a service.
They're consuming the outputs. The customers are seeing this. This blue part is all internal processes that we run. The customers see the output of these engines. They don't get to retrain the model. We just tell them, based on the latest version of the model, you should update to this software version, and you should configure your switches this way, and you should configure your APs this way. But they're not doing the compute.
But the customers are not using the solution to deploy 1,000, node network. They're not utilizing this solution to help them do that. They're utilizing this solution to help them perhaps understand anomalies and deal with, configuration errors or code errors or something. Am I understanding how this is working?
At this moment, that is true, in the sense that if you're going to deploy a network, the network design issues are primarily dealt with human energy. But once you design and deploy the network, these models take over, and there's continuous optimization that is overlaid on top.
I got you. Thanks.
I guess that's the question, because this is all about day two, and my question is more of a day two question. Of I'm a network operator, and I want to programmatically manage my network as code. Does this help me at all when it comes to managing my network as code?
Yeah, so some of these AI insights, you could consume them through northbound APIs. You could get those northbound APIs and then configure some of your network devices to go and change their behavior. But yes, we don't do network design. We don't tell you how many APs you should put in this building, how many switches you need, how many gateways. We don't actually do that. We tell you, once you've actually deployed your infrastructure, how can you change the behavior of it? And we're doing all the compute, and we're just giving you outcomes and APIs to see what you need to change and where. And then we have metrics to tell you how you are doing before and how you're doing after.
Right. So do you create a model per device, or do you bundle a bunch of devices into a single model?
So there's a lot of models running in parallel. There's models that go after device type, there's models that go after AP behaviors, there's models that go around switches, there's models that go around gateways, there's models that go around applications, there's models that are going around events, connectivity problems, Wi-Fi problems, application problems. So think about this as parallel models trying to find issues and tell you what you need to do to fix the issues.
Right, but AI doesn't give you a binary result, right? It's at some point you're going to have to collect the answers from the different models and make a decision. So the more models you have, the more your decision making can become extremely difficult. So eventually, I assume you roll it up based on maybe a network paradigm, or I'm not sure how you do it, but at some point you have to centralize the answer.
Yes, and you'll probably get a better feel when Sri shows you the dashboard. So I'm talking a lot about what's under the hood, and Sri will show you what it looks like at the end. But of course, as you mentioned, we have models around. For example, you have a big box customer. They have 2,000 sites, and we have models that are checking every site. Models are checking the overall site. Models are checking which sites are misbehaving relative to the other sites. Which sites are much worse now than they were 2 weeks ago. And we're generating these anomalies. And of course, you don't want to see these 50 million events. Right. So of course, we're going to have to cluster them and figure out what changed between last week and this week because the stores were doing really bad. And then we have models around all the peers. So there's a lot of big box companies that we have. And we won't actually tell you this, that you have a problem unless you're in the top 10% of problems. I mean, if you're doing better than average, you probably don't want to hear this unless just a report saying you're doing really well.
But yes, I guess that's one of the things I'm confused on is you talk a lot about the models and having the different models, but as a customer, you're just going to tell me what I should do to improve my network. So why do I don't want to sound too trite with this, but why do I care about what's happening under the hood, right? If you're just going to give me kind of the end result of, hey, do this or make this change.
I know you went through the list fast, but I want to draw special attention to this whole peer group, thing in there, because to a large extent, when we see around in the industry, there's a lot of talk about anomaly detection within a particular environment, right? And while those are all valuable, it actually doing just that and stopping there allows you to just identify temporal anomalies, but after a problem shows up and be reactive, right? Yes, I can shorten the time it takes to respond to a problem. But the thing that peer groups helps us, and this is early innovation from Jose and team, even when they were still independent as Rasa, allows us to actually move past the reactive phase and add on a layer of proactive recommendations. Because if I identify a problem in an environment that belongs to, say, customer one, it allows me to quickly say, okay, which other customer environments are in the same peer group, and can I actually quickly realize, analyze to see if the same recommendation would help any of the other similar customer environments in the peer groups, and be proactive about making a recommendation, even if we haven't necessarily encountered that same problem in that particular customer environment. So without doing the peer groups and the environment classification, it's very hard to go beyond the reactive nature of AIOps and to include the proactive nature that we're able to incorporate into our solution here.
Mm-hmm. Yeah, and there's plenty of examples around the connectivity failures. We have a lot of outdoor service providers in our public cloud cluster. Their connectivity failure rate is very high. Their SNI distribution is really poor. We don't want them to trigger anomalies based on what's the normal behavior of Wi-Fi, because they have a very abnormal behavior. But since we have a lot of these, we could tell them, hey, this is normal behavior for outdoor Wi-Fi, and not get anomaly fatigue, and only show them things that are really relevant. That you have an outdoor Wi-Fi, and compared to other outdoor Wi-Fi, these are the type of things they have done to have better outdoor Wi-Fi experience, instead of giving a flood of anomalies that they're going to ignore, of course. Okay, this was trying to layer in the benefit of adding additional data sources. So when you start, you get single customer modeling. And basically what you do is you model based on the data of that one customer, state, stat, events, and configs, what type of models can you build? If this customer is relatively big, you could do models across sites, bad sites, good sites, connectivity clustering things. You could do any temporal baseline changes, but you really don't know how they're doing relative to others. And you don't know if the problems they have is just normal for the environment, or they should be doing a lot better. If you have a lot of APs spaced very closely to each other, and you should be doing very well. And maybe you have configured it out of the box and you're doing 20 megahertz and 5 gigahertz, and given your density, you should be doing 80, and people should be getting 4 times higher speeds for their applications. So the next layering is, and this is not to scale, the anonymized peer data that's used for these AI models is usually 100 to 1,000 times bigger than the data set you'd get when you do only models on one customer. And I know that from having been in a startup, and when you have very small data sets, it's very hard to build interesting models because the models would be very noisy and the baselines would be very noisy, and then you're triggering on noisy models. So having this access to over 1 million devices adds many more use cases. You could compare, as Partha was saying, you could compare peers that are in similar environments, having similar problems, and seeing what they did to solve the problem, and just recommend how to change your state. But then it adds another leg, which is in the bottom here, which I mentioned briefly earlier, is when you have these very big data sets, you start finding very small problems that you won't find if you have a customer with 1,000 devices, which are specific to very esoteric cases that happen 1 in 1,000 times. But when you're going at 1 million devices, then you find these problems pretty easily. And this goes into chipset enhancements, our own software enhancements, and for changing the default configs going forward. Because as Partha was saying also earlier, for example, a lot of the roaming behavior of the devices has changed over the last few years. The way they react to roaming 11v commands, the number of devices that support 11v. Some devices used to be very finicky with network-assisted roaming. So we've learned all those behaviors. We have the behavior of the last 4 years of all these clients and OSs, and how we have adjusted our default configs and how we react to these devices so that they listen to us more and they react better to the commands from the network. The third layer is this customer support cases. We get about 10,000 customer support cases a month. And we're actually running machine learning models on these to actually cluster them for 2 reasons. One is this actually label data sets. We have somebody had an esoteric problem, somebody actually looked at the raw data and came up with a solution. So we have some labeled data of how to solve problems versus a lot of the other data is unlabeled. And another angle is we know what is the most popular support cases. So we could either one of 2 things. One is push a better config for the other peers that should be experiencing problems, or changing the way the software behaves in the next version, so to reduce the number of support cases. And going back to a question I got earlier, I've shown this black box just to show that, okay, you have these inputs, which is data and peers and customer support cases. And the output, I use cases like root causing, recommending, and automating fixes. And the automation question, I think, addresses some of Keith's questions. Some of these are in the early phases of where we could detect something could be improved, and we could just automatically push the config through an opt-in option. So the customer could change the network configs without actually having to go to our dashboards, or without having to consume the northbound APIs and act on those. But what's under the hood of these models is not one big, deep, NN recursive anything. It's all these bubbles represent models, and each one of these bubbles inside it has, of course, a model that's only complex enough to solve that problem. And it ranges all over the place. But the one thing I wanted to make is a hierarchy of models. Some models, what they do is they ingest raw data, they enrich it to be able to provide these user visible models. I mean, they're not user visible, but the outcomes of these end models. And Sri's going to spend some time on basically use cases that are being fed from these higher level models. But under the hood, there's a lot of other power models that know very detailed information about client behavior, AP behavior, environments. So to just go in a little bit more depth of what are examples of models that sit on this low level, which are basically enrich the metadata so that the higher level models could make better decisions. There's things like the environment classifier, which we already talked about a few times. And it could be used both as a classifier or a regressor. We could find new environments that are not very close to any of the 25 we have right now. It may be halfway between 2 environments, and we could actually use it as a regression, say it behaves 50% like this and 50% like that. And then we do a recommendation that's based on a blend of 2 recommendations. But one thing we talked about, and it's related to Niara, is client device type and capability classifier. So each client is interacting with the network. When it associates, it gives us a bunch of information about what it's capable of. And then we observe it as it's connected to see actually if it meets the capability. Because one thing that Partha said about the Nintendo devices, they will advertise that they're 11G capable. But if you don't give them a 1 megabit beacon, they will not connect. So in theory, if 11G, you should support more than 1 megabit per second beacons. But we actually have, through this client device classifier, getting fingerprints from these clients, we know which subset of Nintendos will not connect to the network if you don't set it to 1 megabit per second, the beacon rate. So we know that, and it's actually something that we show the customer saying, hey, for performance optimization, you should do this. And these are the devices that are impacted. Do you want to do it or not? And more often than not, if it's only a few handful of devices that are getting obsoleted, they'll make the upgrade to help them the bigger good, which is in the 99.9 percentile. We've also had similar cases like this where some robots on one of our customers do not support the FS band. So if you look at peers and you look at just environments, you say you have an industrial manufacturing thing, you look at how the behavior of Wi-Fi is in there, and you figure out, okay, based on this environment's number of APs, the density, I should be turning on all the channels. There's way too much co-channel. Guess what? The majority of the devices in that environment do not support DFS. So if you start putting DFS channels on those APs, those clients will not connect. So we have to have, so these low-level models are very aware of the client quirks, client capabilities, client types, OS they're running on. And this actually could be used for some of the profiling and policy later down. And then we have this client mobility classifier. So every minute, every client, we know what's indoor-outdoor state or mobility state it is. And this is important because, for example, a service provider is going to have outdoor service provider is going to have a lot of mobile clients. And if you're in office space, most clients will be stationary. So if you want to build an optimization engine to say what's the optimal config, it's different if you have people just walking by every few seconds across the APs than if they're just going to sit down and do Zoom. So these are low-level examples of classifiers that feed outputs of every client every minute, what's happening, or you could do a lookup on a client and know what it's capable of and what device type it is. And then we have these high-level models. One of examples are, we talked about a few times already, are the configuration type. But then there's, I think, something we didn't touch on as much, which is the day 0, day 1 versus day 2, is the AP density recommendation-like insights. So we know from the network behavior, all the APs are constantly interacting with each other and interacting with the clients. So we know how dense the Wi-Fi deployment is. And we know things about loss and spacing. So we could actually build models that will tell you, if you double the density of the APs, your speed will increase by this much, and your performance will increase by this much, and soon we'll do this much better. So, we all have the problem right now with our homes. We used to have one AP, who cares? Now you have like 5 people at home doing Zoom in parallel. That's my case. And I had to add another AP, somewhere in the middle for the people on the other side of the house. So we have AP density-like recommendations that go after things like coverage holes. So we know about the density of the environment and know about peers. We know peers are doing better, and we recommend you put another AP in your house. Or you have an auditorium based on the metrics, you should be doubling your AP density. So these are recommendations that are more hardware-like, and I think Keith is going a little bit closer to your question. It's not on the switch or on the storage, but it's on the Wi-Fi side. And Bern is going to spend a lot more time talking about connectivity anomaly clustering, so I won't spend any more time. One thing that I don't know if anybody's talking about yet is, since we're ingesting all these, your data, peer data, and customer support cases, and all our bug, actually one thing I didn't mention, we're also ingesting all our internally found bugs. So we could weigh every metric, we could weigh every software version, given on all the customer behavior and their environments, what's the right software to upgrade for you? So each customer could have a subset of features enabled, a specific environment. We could go look at peers, see what software version they're running. Because software upgrade is always a trade-off between, do you want the latest feature, or do you want to sit on something a little more robust? So we actually have a software recommender engine that will look at all these metrics and tell you, hey, given the state, you should upgrade to this software. You'll get more features, and it has very good performance on peers.